I'm glad the expired milk is such a hit.
It's still good.
Well, I tried one earlier. It's like, I don't know.
Oh, I mean, we've had plenty, and I don't think.
Okay.
It's your taste buds. It's not the milk. Is your shake well?
So I want to remind everyone, if they have not already, to get yourself advised for summer and or fall classes. Well, some have, but not everybody. Especially for those of you who are GTAs, because Ms. Sharon wants to know, make sure everybody's signed up for 9 hours and all that. So if you haven't done that yet, make sure to talk to your research advisor if you have one, or academic advisor if you don't, and the academic advisor is likely me. So, but don't let that wait too long. We don't want anyone blowing a gasket. Okay. Are there any lingering homework questions? Shocker. Okay. All right. So, one thing that I just want to put out there that because I know all of you, it could very well be literally all of you, but or a lot of you work together on these assignments, which is perfectly fine. But it's not a good thing if that devolves into just a small subset of you who are actually doing the work, and the others is benefiting from that. And no one likes to be taken advantage of. But also that leads to some of you not really understanding what was going on. And this has happened in other classes, whether undergraduate or graduate, where I can tell, like if someone has written up a solution and then someone else has copied it, and it becomes really obvious that they don't even understand what they're writing, because details get lost and so forth. And if I see that, I'm going to call you out on it, because it's something that just totally hurts you for later. And yes, I do see it at the graduate level. And it's obviously a lot more in undergrad, but so I haven't looked at anybody's homework for yet who's turned it in. Well, very few have turned it in. But that's something I will be on the lookout for when I see it, or when I do get them. So, so don't do that. I mean, you guys are past that level now. Okay. All right. So to mop up from last time. Didn't quite finish this. Landshaw's iteration for A equals B. In the case where A is SPD, symmetric positive definite. So it was a big mess last time to derive all these things, but now I'm going to quickly recap these things without all the gory details, and I'll finally arrive at a coherent algorithm for solving this problem. Okay, so what does Landshaw's do? Like other iterative methods, computes a sequence of iterates, xk, that are converging, hopefully, to the solution x, and they all have this form. Where x naught is the initial guess if you're choosing. If you don't know how to choose it, then you can just go with 0. And qk as this form to be written in terms of its columns. So qk is a n by k matrix. and the columns are orthonormal. So QK transpose QK is a K by K identity matrix. And the underlying principle in designing this algorithm. Oh,
They're calling.
right. Okay. Not music to my ears. We'll hopefully figure it out soon. So the criteria that we're using, really just one, so I use a singular, is, oh, so I guess it's Dr. Harris' class or something?
Yeah.
Okay. All right, so the criteria we're using is that all the residuals, meaning vectors of this form, where you take your iterate and plug it into the system, you want to get 0. What you're going to be getting is something that is presumably approaching 0. All residuals must be orthogonal to one another. An improvement on steepest descent, which, while technically an effective method, only had each residual orthogonal to the previous one residual. We wanted to orthogonal to all previous residuals. Okay. Now, okay. So, in the form of our solution, so I'm going to try to box the essential pieces here. Although it's always a temptation for me to call everything essential, but I'll do my best not to. Well, there are two things we don't know that I have to explain to you. How do we get these vectors of yk, and how do we get these vectors? Because once we have those, we have everything we need. Okay. Now, hopefully there's enough board space for this. Right. So first, how do we get the vectors qk? Because once we have that, describing how to get yk, which yes was derived last time, but that's going to be very quick. Okay, but I'm actually going to show you two perspectives on this that are closely related, because I want you to be aware of both of them. Okay, so initially, I'll set this vector called v naught equal to the initial residual. So now, if our initial guess was a generic 0, then it would just be b. So this happens to be equal to R1, the first residual. Okay. And then I'll set beta naught equal to the 2 norm of v naught, which happens to be the square root of the inner product itself, which will become important later. Okay, then the first vector, the first column of Q, we just normalize v naught. Okay. So we just make it a unit vector. Okay, and for notational convenience only, this is the first thing I did not mention last time. I also have a vector Q naught that is set to be the 0 vector, and you'll see why in a moment. So once we have a first vector in our set, how do we get the rest of them? Using a 3-term recurrence, where each new vector depends on the previous 2. So in other words, this is what I do for setup. Everything I write down below, it's going to be done like in a loop. So we have, I give you these coefficients, alpha k, qk transpose a qk. That's known as a quadratic form, by the way. Okay. And then I can do this. To get the next vector in my sequence, So we see each new vector can depend on the previous two, qk and qk minus 1. Now, what happens, and also, k is going to start at 1 and just keep going. So when k is equal to 1, I have v1 depending on q1, which I have. If I have q0, well, that's why I said it equals 0 there. So we actually, the first time around, we actually don't have this term. But all subsequent iterations, we will. So again, so I can write one formula instead of special cases, because we don't like special cases. Okay. Then, just like I did up here, I normalize vk to get the next q vector. Okay. So, as a result, these vectors, the v's, they are orthogonal. And because each q is one of the v's normalized, the q's are orthonormal. All right, so here we have almost the whole algorithm right here. I do this as a setup, and then I just repeat this. So that's going to give me all my coefficients, my alphas and my betas, that I will eventually need to get yk also. And for this generates all my q's. Questions so far? Now, this is all of this that we arrived at by the end of last time came from orthogonal polynomials, which follow a similar recurrence. So what I'm going to do is I'm going to write side by side with this what's happening from an orthogonal polynomial perspective. Okay. So the same setup. We have a few things we do initially, and then we have a recurrence. So to generate my v's, my first polynomial, g0, is just 1. And then I have beta naught is the norm of g naught, which is the square root of the inner product of g naught with itself. Where, now in this case of vectors, we just have the standard dot product. What is the inner product in this case? I mentioned last time, but I'll repeat it here. The inner product of two functions f and g are R1 transpose f of a, g of a, R1. So that the result of that is a single number. So we define orthogonality of functions as this inner product being 0. Okay. So when we take the inner product, it's just going to be that, which in this case, because g naught is equal to 1, it's just going to be this. And then I define from there my first orthonormal polynomial, each p to be this corresponding g divided by beta naught. And just like I did over here, I'll have a p of a prior index being 0. All right. So then, that's my initial setup. What is my recurrence? Alpha k would be the inner product of pk minus 1. Okay. this again, like on the left side, is for k equal to 1, 2, etc. So inner product of pk minus 1, lambda pk minus 1. And then I define the next polynomial, gk of lambda, is lambda minus alpha k, gk minus 1, minus beta k minus 1, gk minus 2. Then I find the norm, which again is square root of inner product of itself. And then I get my next p polynomial by just taking the g and scaling it, dividing by beta k. All right. Okay, now we're resuming. Okay. Now, how these two are related is that each vector, vk, is equal to gk of a times r1, and qk plus 1 is equal to pk of a times r1. So these are actually, really these are the same process from two different perspectives, computing the polynomials directly or computing these polynomials of a times r1 to get the vectors, which is really what we're after. And for the sake of the underlying problem we're solving, solving ax equals b, that is what we're going to use. Okay. Now, so as a result of this connection between the two perspectives, these alpha k's and beta, these alphas and betas are literally these alphas and betas. They have exactly the same values. They're just, formulas for them are just written differently. But our algorithm is just going to do this. So what this shows is that we're actually computing these orthogonal polynomials implicitly. We never actually need their coefficients or anything like that. So any questions about what happened here? Okay. And these polynomials were made orthogonal to one another. Okay, so actually that's the other thing I want to make clear here. I forgot to write down. So just as the V's are orthogonal, the Q's are orthonormal, the polynomials of G's are orthogonal polynomials. The P's are orthonormal polynomials. So in both cases, if you take the inner product of one with a different one, you'll get 0. But with a P's, if you take the inner product with itself, you're going to get 1. Whereas you don't know that with the G's. All right. So now, if I go back to what we were looking for originally, what?
Obviously. GK is orthonormal, PK is orthogonal. Do I have those flip-floppy?
Flip-floppy.
Okay.
GK is orthogonal. PK is orthonormal.
I can't read your hand.
Yes?
What's the difference in this algorithm and the one we have in the book?
The difference between what and what?
What's the difference
Between this and what's in the book?
and the one in the textbook?
Well, actually very little. Because the algorithm that's derived in the book is actually these steps, but in a somewhat different order. And I need to add a couple more steps. Because that takes me to the next item. I've now shown you how to get the columns of this matrix. I've not shown you, well, I did it last time, but I'm going to repeat it. How do we get this? That will complete the algorithm. All right. Okay. So, So how do we get yk? Really just one step to it. We solve this system of equations. Tk yk is equal to beta naught E1. So that's just going to be a vector that has beta naught as the first element, everything else 0. That's E1. Has only 1 in the first position. And Tk is the tridiagonal matrix that has the alphas and betas in it. So the alphas on the diagonal, betas above, betas below. And this system is relatively easy to solve because this matrix is symmetric positive definite because A is. Oh, I should mention this is also equal to QK transpose AQK. That's what you can use to show that TK is symmetric positive definite. And because it's tridiagonal, or if you do a Cholesky factorization on this, your Cholesky factor only has a lower bandwidth of 1. So solving this system requires order K floating point operations because of that tridiagonalness. Because for a general system, it'd be K cubed. Right. So during each iteration, we're generating our vectors, our Q vectors, to fill this, and we're solving this system to get these coefficients. Because what we're doing is we're taking a linear combination of the Q's to get our iterate, and the coefficients of that linear combination comes from yk. All right. So what I can do now is, well, in fact, yeah. I practically have the entire algorithm written right here without having to change it. I'll need to add one thing. So I'll just erase this to get room, to make room. Okay. Now, the way I've written this is everything's in the correct order. If I had to code this up, this would work. Because I'm making sure that if I do something like this that depends on certain other quantities, then I make sure that those quantities are defined. So for example, I start this out at k equal 1. So I need alpha 1, which requires q1. Well, I have q1 from up here. Then I compute v1. Everything in this line that v1 depends on, I have. From that, I can compute beta 1. From there, I can compute Q2. Then I go back up here. So I'm going to change this to more programming-like syntax and say 4, k equals 1, 2, etc. So I have Q2. Now I go back up here and k equals 2. And I need alpha 2. What does that depend on? Q2, which I have. So I can just keep going. So this is correct. Now, but if you look at the algorithm in the book, slightly different. And here's why. Because in the algorithm in the book, we'll actually carry out these steps in exactly the same order. It's just that it's kind of like I've taken the sequence and cyclically shifted it in a way. Like, for example, okay, suppose here's what I can do. And I didn't really mean to make this different than what's in the book, but I think it's a good exercise to see why they're both correct. Because here's what I could have done. I could have moved this step here, like for example, I could say, I'll put this in parentheses, alpha k plus 1 is qk plus 1 transpose a qk plus 1. All right, and so if I were to like temporarily cross this out and move this down here, everything in the loop is still okay. But can you tell me what, in order to make the whole thing still work, what would I have to add up here? Yes? What specifically? Well, not initial guess, but initial what? Alpha. So what? Yeah. So what should I put here? Alpha 1, because down here, so k equals 1. I'm going to compute v1. I need to make sure I have everything on this line. I don't have alpha 1. I do have q1. I do have beta naught, and I do have q0. So what should alpha 1 be? K with K is what? Q1. Q1 transpose a Q1. Yeah. Then it works again. Because I have Q1, that's fine. So the algorithm, the way I wrote it in the book, was intended to rely on, to do as little as possible for setup and have almost everything in the loop. It doesn't, this is like to try to simplify my presentation. So in the, because I think in the book I pretty much, actually start the loop with this step, the norm, computing the norm. And then I keep going from there. So there are many ways you could write this algorithm that are all equally correct and also equally efficient. You just have to make sure that you have a proper initialization. All right. So any questions about that? Okay. Also in the book, I actually had an explicit k equals k plus 1, which is really just an indexing convenience. So it just cleaned up the indices a little bit. Not absolute. I mean, I could have written it a different way. Because here, like with this for loop, there's sort of an implied incrementing of k. Whereas in the book, just want to make sure I have it in front of me to be sure. I had a while loop. If you're going to have a for loop, it's perfectly okay to assume, and the reader will assume correctly, that your variable will automatically bump up by 1 each time. In a while loop doesn't automatically increment anything. So by putting a while loop, I had to put a k equals k plus 1 in there somewhere. So I put it in the place that led to the cleanest presentation. So, yeah, so all I did initially was I did this, and I also did this. Everything else is in the loop. So, but that's just a personal preference thing. All right, now, I actually don't like the algorithm as it is now. Okay. I'm going to cross this line out. That was just an example of my point. And I want to bring this line back. Now, it still requires a little more setup, but I'm okay with that. Okay. So I'm going to cross this out too. All right. So this is what we're working with. Any questions about it? What's the missing piece? That's a syntax detail. I'm talking about mathematically. If I were to clear this up, MATLAB does not require you put end at the end of a function. So, oh, sorry, what? Someone.
The output.
So what should the output be? Keep in mind the problem we're solving in the first place.
Y.
X.
X. This doesn't produce an X at all. So you try to solve X equals B, and it's like, well, here's all these alphas and betas. It's like when you go to McDonald's and you give you a completely wrong order. So, or if you bought an Apple One and they're like, build it yourself. So, okay, find your soldering iron. Okay, so I need to add that piece. So, and where the best place to put it is right here. After you've computed each alpha. So you should form your TK. Now really what you're doing is you're updating it as you go. So like as you compute alphas and betas, and I didn't really put this explicitly in the algorithm, but there's a reference to TK in there, and it's defined earlier in the text. Here's what TK contains. So you should be building this matrix as you go during the loop. So with that matrix, then you solve the system I wrote down over there. TK YK is beta naught E1 for YK using the best approach. For example, like I said, Cholesky factorization or LDLT. That also works and it doesn't require any square roots. So either way. Okay. And then once you have YK, you can form your iterates. XK equals X naught plus QKYK. And now you're producing a correct output. And what you would do is, what I also haven't explicitly mentioned here, because like in the book, it says, like, while not converged. So this loop will keep going until you determine that XK has converged. So for instance, you could check the difference between 6, or you can compute the residual and check the size of it. There are different things you can do to check whether this is converging. Like you have to choose some tolerance, like xk minus 1, the norm of it is less than, say, 10 to the minus 8. So you have some leeway here. So that's why I'm not specifically writing anything down. The point is, you feel like you're not going to make any more progress. And if you don't need a particularly accurate solution, you don't really care for your application, you can stop earlier. Like, say if you minus 3 or something like that. Okay, so that's it. This is the whole algorithm, Lanshaw's iteration. So it'll produce the sequence of iterates that will converge to the solution of AX equals B. And these vectors, BK and QK, they are not equal to the residuals, but they are parallel. They're scalar multiples of the residuals. And because they're orthogonal, that means the residuals are all orthogonal too. So any questions about what happened here? Yes?
So, TK is dependent on QK to find the betas and the alpha.
Right.
Yeah, so before that, we need to compute QK outside.
Oh, well, the thing is, since this is happening in here, so for example, let's suppose k equals 1. So you go ahead and compute alpha 1. So now you have T1, which is just a number alpha 1. So then you solve this 1-by-1 system for Y1 and compute X1.
So the QK is from what do you call it? The QR is the composition.
No, there's no QR happening here. Are you talking about capital QK?
Yeah, no, that's the small one.
Well, these are the columns of this matrix.
I got it.
Yeah. Okay. So I could write it this way. that. Yeah, so I could say, so you can do it that way. Yeah. Okay. Whoops. Other questions? Well, also the matrix TK, you would not want to form it as a two-dimensional array because most of the entries are zero. That'd be wasteful. Like I talked about banded matrices, you represent it using the three vectors as diagonals. That would be better. Actually, two vectors, because the ones above and below are the same.
Is it okay to make it a tridiagonal? Because it always has upper bandwidth 1 and lower bandwidth 1.
Well, yeah, yeah, exactly. That's why you can use vectors to represent them. So that for a storage point of view, that would be best. So then, if you do like Cholesky factorization, you'd have one vector for the diagonal and one more for the subdiagonal, and that's all you need. Yeah, so really, two vectors is enough to do the whole thing. Well, that's the sort of thing that when you're first implementing this, like say if you're going by what I've written on the board here, you don't have anything else. It probably would be best to go ahead first time, implement it using go ahead and use a two-dimensional array, knowing it's not necessarily efficient, but at least make sure it's correct. Then, once you know it's correct, you back up, you save that code, and then try to make it more efficient by going to maybe three vectors, making sure it still works. Then, once you have that working, and you see that the two vectors for diagonals are actually the same, then you can cut down to two vectors. And so, the famous Donald Knuth, who is a professor of the art of computer programming so retired from Stanford. So yes, I've met him. His famous saying is, premature optimization is the root of all evil. So if you go for the most efficient implementation from the very beginning, that turns out to not go well because you may be sacrificing correctness. Go for correctness is always most important. Like when compilers, you give it your C++ code and it produces a machine language executable. It will do a lot of things to try to make the code as efficient as possible, but it will gladly sacrifice possible optimizations if there's any chance it might jeopardize correctness. You cannot sacrifice that. So that's something to keep in mind as you write code, whether it's for this class or another class or your research. Correctness first. You can always go back and make it more efficient later. Okay. All right. Now, all right, so now I'm going to spend all this time talking about this method. Okay. So now I got to tell you what's bad about it. Just like I did Gaussian elimination, spent all the time in Gaussian elimination, but I told you why it's terrible. And it's led to iterative methods. And it's not universally terrible, but that's the overriding thing in numerical analysis. That's actually why I appreciate the field so much, because it's always possible to do better. Oh. Okay. Still going? Okay. So now I don't want to totally shaft this stuff, talk trash about this algorithm, but it took all this time to derive. So the pro is it is a substantial improvement over steepest descent. because you're not going to have that zigzag thing going on. Even in the case where it's certainly if a matrix A is ill-conditioned, Langelo's also run into trouble, but not as much trouble as steepest descent. So because and this is due to orthogonal residuals. And in fact, I can say that the number of iterations should be less than or equal to n, the size of a matrix. And the reason for that is after you've carried out n iterations, this vector, Vn, should turn out to be 0. And what will happen is that, so therefore, beta n will also be 0. So then you can just use Tn to solve the entire system. In fact, you could say that this system right here, this system right here is actually what's called a similarity transformation of Ax equals b. So in this extreme case where k equals n. In fact, at any time, suppose it happens earlier that like beta k is 0. That's actually a good development, as long as you don't do this, divided by 0. So if beta k is equal to 0, then your previous iterate is exact, except for round-off error. So you always have to worry about that no matter what. So it's funny thing is we call this an iterative method, meaning a method that could conceivably carry out any number of iterations off to infinity. But it's really not. It's actually just another form of direct method, like Gaussian elimination. Gaussian elimination, you know how many iterations in every case you're going to need. So we kind of have that here. But this time it's different because iterative methods are primarily for matrices that are very large, like maybe millions of rows and columns. So saying that this will terminate in n iterations doesn't really mean that much because the point of an iterative method is you actually want to perform far fewer than n iterations and at least get reasonably close to a solution. So saying, oh, this will stop in n iterations, that's not really anything to get excited about. Okay. But again, still an improvement on steepest descent, something that at least has a guaranteed termination. What's bad about it? Well, one thing that kind of undercuts this point here is you can have a loss of orthogonality. In the QK. And they're supposed to be orthonormal, but because of how round-off error can accumulate, in practice, that can end up not happening, and it can really throw things off. But you can re-orthogonalize. In other words, you can force. Like you can perform Graham-Schmidt orthogonalization to make them be orthogonal and keep going. In fact, people have shown how you can figure out analytically when it's going to be a problem and then carry out. You don't have to do it every iteration because that's expensive. So that's a problem, but people know how to fix it, so it's not a big deal. This next one is a big deal. This step, solving this system, well, this matrix is growing. You're solving a larger system each iteration. Now, when it's 1 by 1 or 2 by 2 or 3 by 3, who cares? The effort is negligible. But what if you carried out 100 iterations? Now you're solving a 100 by 100 system. So each iteration gets more expensive than the last. So that's something that's a problem. Also, you need all of these Q vectors because of this summation. So your storage requirements increase also. So that's bad. So as a consequence of this, you don't have a way to express your solution in this form, where you can say your new iterate is equal to your previous iterate plus something. I don't have that. I have this. My current iterate is equal to my initial guess plus something that's growing in complexity. So I want to have this situation. In fact, for all I dumped on steepest descent, at least the steepest descent, I did have this. Each iteration comes directly from a previous one. I don't have that here. So I got my orthogonal residuals, but then I had to give up that nature of non-stationary iterative methods, where I'm at a certain point, I find which direction to go, I go there, and then I figure out my new direction and go from there. So I've lost that by getting these orthogonal residuals. So because I don't have this, I now have to incur greater expense, computational expense in each iteration, and also greater storage in each iteration. So it'd be nice to be able to do something about that. And how much time do I have to tell you about it? I have 39 minutes. Okay. Now, so how we deal with this leads to what is called the conjugate gradient method. Now, the last time I taught this class, I went through what was then my notes, because the book wasn't done yet, and did the whole gory derivation of every step of conjugate gradient. It took me 3 class periods to do it. I'm not doing that. It's in the book, you can read it. What I will do is give you the essential properties, give you an idea of how it's derived, because, and that's what I really want you to know anyway, and the devilish details kind of can easily distract from that. So a fix for these problems I listed over here is the conjugate gradient method. Also known as just CG. That's in the next subsection. Okay. Now, you can think of it as, again, a fix for steepest descent that, but it uses ideas from Lanczos to carry it out. So I want to recall the main step in steepest descent. That each new iterate is equal to the previous iterate plus some constant. So this is not alpha from Lanczos, so don't even go there. Times a search direction, which was the residual. Actually, using a notation I've had lately, it's RK plus 1. Where alpha k is chosen to make each residual orthogonal to the previous one. So RK plus 1 is orthogonal to RK. But it is not orthogonal to previous ones. Again, steepest descent has no memory. So I bring it back to, so I can easily show you the contrast between that and conjugate gradient. So for conjugate gradients, each step each new iterative is equal to a previous one, like in steepest descent, plus some constant, that's actually the Greek letter nu, not a v. What do you call it, fancy v? So, similar form, each iterative is a previous one plus a constant times a search direction. In steepest descent, I just chose the search directions to be the residual, because that's the literal direction of steepest descent. Here, my search direction has this form. It's a residual again. Actually, what I'm going to do here, I want to unify this presentation. I'm going to shift my indices. So now we have the same RK in both cases. So, actually, this is still correct. So, the search direction is the residual again, but I add another term on here. Some constant times the previous search direction. So, PK, PK minus 1, those are search directions. RK is still the residual. So you can think of this as a correction to steepest descent in order to avoid the problems that steepest descent has, to avoid that zigzagging effect. But now I need to explain, I have these two constants I have to figure out each time instead of just the one that I had here. Now this constant was chosen to make each residual orthogonal to a previous one. What is my criteria for choosing these constants? Thankfully, it's very easy to describe. So, nu k and mu k are chosen to ensure these properties. All of the residuals are still orthogonal, just like in Lanczos. But what we really need are the search directions to have some kind of orthogonality. Now, it'd be nice if the search directions could also be made orthogonal. That's not really practical. But we're able to get something that comes close. The search directions satisfy this. Pi transpose APJ is 0 if I is not equal to j. Now, if the A was not there, I'd have Pi transpose Pj equals 0. That would be orthogonality. So I don't have orthogonality. I have what is called, they're A-orthogonal. So now, anytime you have a symmetric positive definite matrix, like A, you can use that to define an alternative notion of orthogonality. So if they're not orthogonal, they're A-orthogonal. Or, alternatively, the term is A conjugate. So the fact that these search directions are at least A conjugate, which means the same as A orthogonal, and the fact that they are based on the residuals, which are gradients, that's where the name comes from, conjugate gradient method. So the search directions, you can think of them as gradients that are corrected in such a way to be conjugate. So that's the etymology of a method. Okay. So what you would see that's written down in the book is like how to get the formulas for these constants. Like, for example, what I could do is I could like multiply both sides of this by a and take the inner product with, for example, pk. If I multiply this by a and then take the inner product with pk, then this term would be 0. Actually, I wouldn't want that then. I'm trying to solve for this. If I multiply both sides by a, take the inner product with pk minus 1, this term would be 0. And then I have an equation that I can solve for mu k. So there's, as you can see in the book, there's a whole mess of manipulations carried out to get the best formulas possible for these constants. But all of that is driven by trying to satisfy this criteria. So enforcing these gives you the equations that you solve to get formulas for these guys. So in a nutshell, that's what's happening on those god-awful pages, which if I try to present that now, by the time class is over, your ears will be bleeding. So, like I said, 3 whole class periods last time. Okay. So what I will do is show you the actual algorithm for conjugate gradients. So you try to solve A is equal to B. You're given A and B, and let's assume you're also given some sort of initial guess, which might be 0. Okay. So, found something that, well, not a mistake technically, but something that doesn't need to be there. Yeah. By the way, on my web page, like there's a link to the left that says textbook. If you click on that, it shows there's a list of mistakes that I've found so far. So, and I'm finding several in this chapter. So, if you want to stay up to date on that. So I compute my my initial residual based on my initial guess, and then I have a for loop. I think I might have had a while loop originally. It actually said k equals 1 up top. But now it's a for loop, I don't need to do that. So in fact, the other algorithm. So yep, I'll have something else to add to the list. Again, not a mistake, but definitely an inefficiency. So I'm really hoping that my publisher will let me do a second printing of this book. I don't want to be like calculus books and have a new edition every 2 years. I couldn't advise my students anymore. I'd be busy writing books. Okay. Well, I'm doing a Python edition of this book, so hopefully by sometime next year. Okay, so in my loop, so I need an if statement. The cases k equals 1 or greater than 1 are different. So to compute my search directions, okay, so I have that. And then that gives me, so this is the coefficient that I need to get my search direction. next, if I'm on my first iteration, my first search direction is just the residual. So in fact, the first step of conjugate gradient will be equal to the first step of steepest descent. But then after that, it's going to deviate. Okay. After that, I need to perform this one matrix vector product, the only one I'll need in the algorithm. And then I get my other coefficient, nu k. So formulas for my coefficients, nu k and rk, are actually fairly simple. So notice the denominator in that one is pk transpose apk. But A is symmetric positive definite, so that quantity is always going to be positive, so we don't have to worry about division by 0, just like in steepest descent. Now I have my coefficients. I can update my solution. And I can use the same coefficient to update my residual. That's it. That's the whole algorithm. It seems deceptively simple compared to all the work that went into deriving it. Now, I should mention that the iterates that it computes are actually exactly the same as the iterates that Lanczos iteration computes. The xk's will be no different. But notice we're not solving any system of equations here. The most expensive operation is this one, the mat vector, or matrix vector multiplication. But we're not solving any tridiagonal system. So each iteration is exactly as expensive as the previous one. We have no onerous storage requirement. Notice we do need rk and rk minus 1 and pk minus 1. So we need those most recent search directions and residuals. But all the ones that came before that don't need. So the amount of storage needed does not grow over time. The amount of work per iteration does not grow over time. So while it produces the same solution as Lanczos, or approximate solution, it does so much more efficiently in terms of floating point operations and storage. So this is why for a symmetric positive definite system, people use this. So the amount of work per iteration is order n squared for this matrix vector multiplication. Now, the number of iterations should be at most n, so we're talking order n cubed altogether. But usually conjugate gradient is used for a case where A is sparse. So it would probably take less operations than that, like maybe on the order of n squared rather than cubed. Also, hopefully you're going to do far fewer than n iterations, because n is likely to be large. So questions about conjugate gradient? It's going to quickly just present this method when you leave out the terrible details. But I want its main properties to stand out. Okay. Now, what's wrong with conjugate gradient? See, there's always something wrong. There's always something that can be improved. And it's definitely the best method I've shown you so far. But if A is ill-conditioned, again, if there's any iterative method, it's going to converge a whole lot more slowly. So in fact, there are results about like formulas for error estimates that depend on the condition number of A. And that show that if the condition number is large, the error goes to 0 very, very slowly. But again, there's something that we can do. And it's called preconditioning. The idea is you transform Ax equals B into an equivalent problem that hopefully can be solved by conjugate gradient more easily. And I think I have just enough time to show you. I would like to show the algorithmic details. some of them. Now, what you do is a problem AX equals B becomes this problem. A tilde X tilde equals B tilde, where A tilde equals C inverse A C inverse. I'll talk about C in a moment. X tilde equals Cx, and B tilde equals C inverse B. And if you plug in my definitions of A tilde, X tilde, B tilde into here and simplify as much as you can, it simplifies to AX equals B. So the two problems have the same solution. Okay. So what you want is A tilde to be closer to identity. So if there's a way to do that, which I'll talk about at the end, that would lead to a much better conditioned system. And you're still going to use conjugate gradient on it, but hopefully it'll converge much more rapidly. So what I'm going to do is, okay, I'm going to take the same algorithm but applying it to the new problem, and I'll show you what can be simplified. Hopefully I'll get this right. Oh, good, I do have it written here, so I won't screw it up. Okay. So I'm just going to repeat this, but I'm going to fill in the transform problem. So I would have R1 tilde, but what is R1? Okay. That's going to be B tilde minus A tilde X1 tilde. Now, B tilde, for my definition over there, that's C inverse B, minus A tilde, which is C inverse A C inverse, and then X1, oh, sorry, it's X0. Okay. Well, that's going to be C X0. So C inverse and C cancel. So that's going to be C inverse B minus AX0. So even though I'm solving the tilde problem, A tilde X tilde equals B tilde, I want to express everything in terms of the original variables and also the matrix C. So this is my starting point, C inverse. Now, I have my loop, my if statement. Okay, so what's going to happen here is I compute my mu k, and here's what I do. Wherever I see an R, because notice this R is equal to the original R times the C inverse. So that's what I'm going to do here. Wherever I see an R in the original algorithm, I'm going to put a C inverse in front of it. So I'm going to have C inverse RK transpose C inverse RK. And then same thing for the denominator. C inverse RK minus 1 transpose C inverse RK minus 1. Okay. Now, using a property that the transpose of a product is the product of a transposes in reverse order, what that gives me is RK transpose C inverse RK. But what does that simplify to? Yeah, c to the minus 2. So I'll put that in here. C to the minus 2. And same thing in the denominator. RK minus 1 transpose C minus 2. RK minus 1. Okay. Then, wherever I see, okay, so residuals in B, I multiplied by C inverse. X's or P's, because notice X and P's are related to each other. I'm going to fill in a C in that case. So I'm going to have CPK is equal to C inverse RK plus mu K C PK minus 1. So P's and X's are multiplied by C. R's and B's are multiplied by C inverse, based on this. Now, what I can do is I can multiply both sides by C inverse. So that cancels out the two C's, and I get C to the minus 2 again. So I'm going to circle those. These will be of interest. Oh, this too. That's my first part of my statement. And the else part is CP1 is equal to C inverse R1. That's the same as P1 is equal to C to the minus 2 R1. So there's that C to the minus 2 again. Keeps popping up. Okay. What about the rest of the steps? Same multiplication conventions. So anything that's multiplied by A, we multiply by C inverse. VK is equal to APK. And there's C inverse there also. Okay. Although really, those will just cancel. You don't really need those. Okay. What?
The previous one you said P's are multiplied by C.
Wait. But there's an A here. That changes it. Yeah, think of it this way. Things that are in the range of A can multiply by C inverse. Things that are in the domain of A can multiply by C. Because of follow that. All right. Okay. That's just R1. Okay. Now, but notice I have R1 tilde equals C inverse R1, but you don't see me using R tilde one down here. So I don't really need it. Okay, next step. Computing new K. Same thing with residual. RK transpose C to the minus 2 RK over CPK transpose C inverse VK. What's going to happen here is that this C will cancel with this C inverse. So I won't actually need those. After I do the same kind of thing I did here. CXK, CXK minus 1 plus new K CPK, but every term has a C in it, so we just cancel them out. That was a waste. Last step, residual C inverse RK plus 1 is equal to C inverse RK minus new K C inverse VK. But there again, we have C inverses in every term. So it turns out that what actually changed? I'm going to circle what actually changed. here, 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 and here. Notice every single change is c to the minus 2 times residual vector. So now what I'm going to do is I'm going to clean this up over here. Oh, whoops. To anyone who watches this later, that's what happened. Sorry about that. Okay, and yep, I'll be able to finish in time. To get preconditioned conjugate gradient. Okay. But you'll see it's not much different than the original in terms of the form of the algorithm. Okay. So we have a residual just like before, and I need to make a little room here. Okay. So I need to rewrite that. R1 equals B minus AX naught. Here's your guess. Here's my for loop. Okay. And then I might step in here, solve this system. M zk is equal to rk, where m is equal to c squared. So that means that zk is equal to c to the minus 2 rk that we see in all these circled parts here. So then, for the rest of the algorithm, in certain places, all I need are my z's in place of r's. So I would have rk transpose zk. And down here, rk minus 1 transpose zk minus 1. So any place where you see a c to the minus 2 r something, you just replace r with z. And I need that here too. And that's it. That's preconditioned conjugate gradient. So in terms of the work involved, we do have something significant, unfortunately. This. We have to solve a system of equations in each iteration of solving the original system of equations, which sounds kind of bad, kind of stupid, actually. That's why you have to be careful how you choose a preconditioner, and why this is typically used only for systems that are sparse. You have to choose M so that this system is a whole lot easier to solve than the original. And if you do, and still a good preconditioner in terms of making a problem closer to identity, in terms of a matrix, then hopefully you'd only carry out a few iterations. You'd only have to solve the system a few times. Because that's what you're trying to do. You're trying to cut down the number of iterations. So you have to choose M so that the more expensive iterations, so in other words, fewer, more expensive iterations adds up to less time overall than more, less expensive iterations. So there's a trade-off here, and you want to choose M that puts you on the winning side of that trade-off. Okay. Now, we don't have much time left anyway, but now preconditioning is actually a very active field of research in numerical linear algebra. Lots of people are working on coming up with better preconditioners. There's many approaches out there. Also, people are trying preconditioners that are problem specific. So, for instance, if you're solving a PDE, if you know your matrix comes from a differential operator, knowing that may help you come up with a good preconditioner. So, I'll just mention one relatively simple idea real quick, and then I think you'll have suffered enough for today. Oh, by the way, I've not chosen problems from this chapter. I still have more chapter 5 material on Monday, and then that will be finished. So, and Monday is when chapter 4 homework is due. So, so I'll by Monday we'll have problems chosen and also a quiz put up. So an example of a preconditioner. That's simple to describe. is incomplete Cholesky. So the idea is, okay, so you choose, make sure I have this right here. All right. Do I have this described here? Oh, yeah. M equals H transpose, where A is approximately equal. So this is like approximate Cholesky factorization of A, where H is forced to be sparse. For example, you could decide that if A is a sparse matrix, like you could try computing the actual Cholesky factorization of A, but any entries of A below a certain threshold you just treat as 0. And as a result, presumably H would come out sparse, more sparse than the true Cholesky factor. So in that case, because since H transpose would be a symmetric positive definite matrix, then it would have a matrix that actually is its square root. So it is a square of some matrix C. So it still has a proper form of a preconditioner. So because that's one well-known result, that any symmetric positive definite matrix has a real matrix that is its square root. So now we never actually compute the matrix C at any time in the algorithm. We only work with M. But M can be expressed in this form, where this is something we can actually compute. So what you do is you assume Aij is 0 if the entry is below a certain threshold. Or you may decide to do the same with H, like all entries of H below a certain threshold, you 0 those out. And so that would be, again, approximate Cholesky factor. So that's one relatively simplistic approach to preconditioning, but there's many far more sophisticated methods out there. And certain preconditioners are available in MATLAB. So in MATLAB, the function PCG implements preconditioning conjugate gradient, where you have the option of specifying a preconditioner, but then you have to choose what preconditioning method yourself. And there actually is a MATLAB function that helps you do incomplete Cholesky. It's just a real pain to use. So, okay. Yeah, but any of the iterative methods that I'm covering in this chapter have MATLAB functions that implement them. So because we have this multiplication with A each time, like all of these, so residuals fall within a Krylov subspace. They can all be expressed as polynomials of A times the initial residual. So that we don't have an explicit Krylov subspace from this algorithm like we do for Belanchos iteration, but technically conjugate gradient is also a Krylov subspace method. There are other Krylov subspace methods, many of them, and so I've completed my discussion of iterative methods for symmetric positive definite systems, but there are also Krylov subspace methods for more general systems. So that's what I'm going to talk about on Monday. How do we handle a case where A is not even symmetric, let alone symmetric positive definite? And we'll also talk about the case where A is still symmetric, but not positive definite. So it turns out the Lanczos iteration will still be useful for that case. So basically, I'm going to be generalizing Lanczos or conjugate gradient to these other kinds of problems. So then you'll have a good rundown of what Krylov subspace methods are out there. And then if you go to a conference on numerical linear algebra, you'll have a better idea of what they're talking about. So, okay. It's 6:14, so I don't see any bleeding ears, so we're good.